Let us begin. Right, so far what we have seen is ordinal numbers, right? So today we want to study a subclass of ordinal numbers which are called initial ordinals. So say that alpha in On is an initial ordinal if for all beta in On, beta less than alpha implies that beta is not equinumerous with alpha. Okay, so for example, 0 is initial. What is less than 0? Nothing. So therefore, well, this property is automatically true. Yeah, for all beta less than alpha, the conclusion holds because there is no such beta. What about 1? 1 also the property is true. Does there exist a bijection between 0 and 1? No. Yeah, bijection exists between two finite numbers if and only if they are the same. Yes, pigeonhole principle. So 2, 3, all of them. What about omega? Does there exist a bijection between something small, strictly smaller than omega and omega itself? What is strictly smaller? Something finite, something natural. Okay, so natural number and omega, because omega is infinite, natural number is not infinite. So omega. What about omega plus 1? Is it an initial ordinal? No. Yeah, because omega plus 1, yesterday we saw that omega plus 1 is in bijection with omega. Very good. Omega plus omega. Omega plus omega is also in bijection with. So if you remember the green parenthesis, everything in those in one green parenthesis is in bijection with each other. So what will be the next element? What will be the next one? Omega 2. What will be the next one? And then omega sub, then omega sub plus 1, and dot dot dot, like for every ordinal alpha there is omega sub alpha. Yes, so for every ordinal alpha, the ordinal omega sub alpha is an initial ordinal. So how many initial ordinals are there? As a consequence just by this statement, as many ordinals plus, yeah, plus 0, 1, 2, 3 up to. Yes, so those are not indexed by ordinal numbers. Yeah, those are just natural numbers, and after that we have omegas. So omega is actually omega sub 0, right? Then omega 1, omega 2, etc. Okay, so basically, therefore, there is a proper class of initial ordinals. Okay, so here what is there to note? Look at omega. Omega is the least infinite initial ordinal. Correct? So let me write that. See, least elements exist in every ordinal, but least elements also exist for every non-empty subset of On. of the class of ordinal numbers. So let me write that. So omega is the zeroth or first, I mean whatever you want to call it, first infinite initial ordinal. What is omega 1? Second is the second infinite initial ordinal, or equivalently first uncountable initial ordinal. So I can list them. See, this is the property of ordinal numbers. I can always list them. This is the zeroth one, this is the first one, this is the second one, this is the omegath one, this is the omega plus 1th, omega plus first, then omega plus second, and so on. So I can always list them. Yes?
So omega substitute omega 1 won't be again countable, so you can't list them again.
What won't be countable?
Like the subscript of omega 1.
Right.
It won't be countable. So
It won't be countable, but still you can list it. See, listing just means that I should be able to tell you that this is 0, this is first, and dot dot dot. It should be indexed by ordinal numbers. Listing means indexing by ordinal numbers, yeah. Setting up a bijection with one ordinal. So that is listing. Yeah, because finite listing we all know what to do. But infinite listing, ordinal numbers are our tools. Yeah, any question about this? Omega 1 is the first one, second one, then omega sub omega is the omegath one, then omega sub omega plus 1 is the omega plus first infinite initial ordinal. We can list them. So basically what we are doing, we are choosing, like when we are finding this, yeah, we are taking the collection of all infinite ordinals, or all infinite initial ordinals, then we are applying that it is a well ordered class. So it must have a least element. Well, this is the least element. Then I remove that element. Then I ask the question, is it non-empty? Is the collection of infinite initial ordinals apart from omega non-empty? Yes. So therefore again I can find the least one. Then I keep removing them one by one. Then eventually I am left with no omega sub n. Then I again ask, is the collection of infinite initial ordinals non-empty? The answer is yes. Well, the next one will be omega sub omega. And that's how we proceed. Understood? So, normally in natural numbers we have a shift map, correct? Shift map tells you that if I know 0, then I know 1. If I know 1, then I know 2. Similarly, there is a shift map here. If I know 0, then I know omega sub 0. If I know 1, then I know omega sub 1. And omega sub 1 is always bigger than 1. Omega sub omega is much bigger than omega. Omega sub alpha is much bigger than alpha. Understood? Okay. Now, let's proceed. I mean, maybe I will write just this statement is the omegath infinite initial ordinal. Now, I am ready to define cardinal numbers. So, what's our tagline for ordinal and cardinal numbers? Ordinal numbers describe position in a list, whereas cardinal numbers describe size. Okay. So cardinal numbers are same as initial ordinals. Yeah, I mean this is equal to, after forgetting, this is, I mean the definition of a cardinal number is simply an initial ordinal, but I am writing something more for you to understand. After forgetting the well ordered structure, we don't need to remember it. So every ordinal, how do we write that? Well, omega, this, right? So that number is now as a cardinal number. I will forget about the ordering, I will only remember omega, but now I have a different notation for that, and that notation is aleph naught. How to draw aleph naught? It's a Hebrew letter, yeah, first Hebrew letter, aleph. Yeah, this is how is it pronounced? Aleph naught. Okay, this is the pronunciation of naught is same as NOT. Okay, aleph naught. It's a Hebrew letter, and how to write that? Write two vertical tildes and then join with a line. Aleph 1 is the next one. So I will forget from omega 1, I forget that it had this belonging relationship which was which made it a well ordered structure. I will only remember omega 1 as a set, and that one is aleph 1. So in general I have omega sub alpha, yes, so that will be called as an ordinal number, I will call it aleph alpha. So all the infinite, as a cardinal number, all the infinite cardinal numbers are denoted by aleph naught, aleph 1, aleph 2, aleph omega plus 1, in general aleph sub alpha for every ordinal alpha. That is my collection of cardinal numbers. And I will say that let Cn denote the proper class of all cardinal numbers. I hope there is no confusion why it is a proper class. Yeah, so what does it contain? Cn is equal to omega union aleph sub alpha such that alpha is in On. See, what are the first initial ordinals? These ones, they are elements of omega. And then the next ones, well, if I replace omegas with alephs, then I will get all the cardinal numbers. So that's precisely what I have written here at the bottom. Yeah, cardinal numbers is the class of finite cardinal numbers and infinite cardinal numbers. Any questions so far? Okay, so let us proceed. Now, what I have done so far is define cardinal numbers, but still I haven't described the function which assigns to a set a cardinal number, right? Its cardinality. Given any set, I should know how many elements are there. Yeah, its cardinality. Now, what properties should this function have? I mean, first of all, it should be a function. So every set should get a unique cardinality. Correct? Okay, so now we want to describe associate a cardinality to each set A. What will be the cardinality? It will be a cardinal number. But before we do this properly, we will need to assume one more statement. Yeah, that is an axiom, or I mean its normal terms, it's called a theorem. I will tell you its history. It is called well ordering theorem. In short, WOT. Okay. Let me write it down first and then I will explain the history of this statement. So, it says that given any set X, there is some linear ordering, a strict linear order, yeah, some strict linear order less than on X. What is the meaning of this? What is a strict linear order? Not belongs to. It is irreflexive and transitive. Yeah, okay, so i.e. This less than is a subset of what? X cross X. Okay. Is irreflexive and transitive such that X comma less than, now this will become, is a well ordered set. Okay, what am I saying? Given any set, there exists an order relation, strict linear ordering on it, which makes it a well order, which means I can find the least element. If this happens, then I can take the entire set X if it is non-empty, correct? I can take entire X, then I can find out the least element because it's non-empty. Well, I remove that. So the least element, yeah, I mean this is the whole statement, yeah, well ordering theorem says that every set can be well ordered with respect to some ordering. So if I can do that, then what can I do? Well, x0 is minimum of X, yeah, minimum with respect to less than ordering. So let this x0 be the minimum of X. Then x1 be the minimum of X minus x0. X minus x0, if it is non-empty, then I can define its minimum. I will call that x1. How will I define x2? Minimum of X minus, not x1. See, I don't want to get back x0 and x1, right? So as long as, so x0 and x1, then I will continue doing this. So maybe I have an infinite set and I have exhausted all x0, x1, x2 up to xn for each n. Then what next can I do? I can define x omega to be minimum of X minus the collection of xn where n is less than omega. Yes. Then I can define, well, if this set happens to be non-empty, yeah, if after removing x omega from this set, if it is still non-empty, then I can define x sub omega plus 1, which will be minimum of X minus, well, I will write x sub beta where beta is less than omega plus 1. Okay, so in general, now you can see what is the pattern. I can describe x beta equal to minimum of X minus, I should say this is alpha. X alpha, I will describe it to be x minus x beta such that beta is less than alpha. If x minus x beta such that beta less than alpha is non-empty. So if I define zeroth element, I remove the zeroth element, then I am left with a minimum again. If it is non-empty, then I can find the minimum. If I further remove that element, then again if it is non-empty, I can find the next element. So understood this procedure? So this is a transfinite recursion, transfinite recursive definition for listing elements of capital X. So what is well ordering theorem saying essentially is that you can list all of its elements. This is the zeroth one, this is the first one, second one, third one, omegath one, omega plus one first, and dot dot dot. And how far can we go? Well, only as far as this process doesn't terminate. When will this process terminate? If x minus like we have listed all the elements. As soon as we have listed all the elements, the process must terminate. So I can list the elements of every single set. Now when this was first proposed, so this well ordering theorem was proposed by Cantor. He said that this is like an essential principle of thought. Everything can be listed. And he thought that he had a proof. He wrote down that proof. The proof was obviously wrong. Right? It's an essential principle of thought that even if I'm given real numbers, I can say this is the 0th real number, first real number, second real number. Well, nobody wanted to believe him. Can you list all real numbers? Yeah, we have a feeling that real numbers are continuum. Yeah, between any two real numbers there is another real number. So how does it make sense to have a list of all the real numbers? So therefore, Koenig, this was before 1900. So Koenig, a Hungarian mathematician, he gave a proof that reals cannot be listed. This was around 1904. Yeah, reals cannot be listed because real numbers, they don't have. See, when we say real numbers can be well ordered, the warning is that we are not well ordering it with respect to the usual linear ordering. The usual like pi is less than 4, 3 is less than pi, that kind of ordering is not there. What it says? Sum. Yes, so that's a warning. Maybe I should write it here. Warning. Well ordering of reals is not the usual ordering. This was a big point of conflict because rational numbers can be well ordered, that people could show easily. Yeah, it's not with respect to the usual ordering, but we have seen rational numbers can be listed. Yes? So that wasn't a surprise, but real numbers can be well ordered. Yeah, people did not want to believe that. So therefore, Koenig gave a proof that reals cannot be listed. A few days later, Hausdorff found a flaw in that proof. Hausdorff found a flaw. So therefore, well, the question was still open. Yeah, people did not want to believe that reals can be well ordered, but the so-called proof that it cannot be done was wrong. So now what to do? So eventually Zermelo-Frankel set theory gave a proof using the axiom of choice. Okay, so well ordering theorem is also known as Zermelo's theorem. But as I have repeatedly mentioned in this class, that axiom of choice can neither be proved nor be disproved. So if we want to assume axiom of choice, then we can prove well ordering theorem. That's what Zermelo showed. In fact, it turns out that well ordering theorem is simply an equivalent statement of axiom of choice. Okay, so maybe I'll write it here. In fact, modulo ZF, modulo means always assuming, yeah, modulo ZF, AC is equivalent to the well ordering theorem. Next week sometimes I will give you an entire lecture on axiom of choice and its equivalents. Okay. So this is simply axiom of choice. Yeah, well ordering theorem is a different statement, but we need some more background before we can go to axiom of choice, like Zorn's lemma, which is also another statement of axiom of choice, and then we'll see the equivalence of all of them. So, okay, coming back to the first line, what do we want to do? Associate to every set its cardinality, but we are only going to do by assuming well ordering theorem. Yeah, we cannot describe cardinality otherwise. So assume WOT throughout this lecture. As long as we are talking about cardinality, then we have to assume well ordering theorem. And the question is why? Yeah, so why is because of this reason. So given a set X, define S of X to be the collection of all those ordinal numbers such that alpha comma belongs to is isomorphic to X comma less than for some well ordering less than on X. Okay, so for example, let X be 2 comma 3. What is S of X? Does everybody agree with that?
Yeah, like everything which is isomorphic to 2.
Everything which is isomorphic to?
Oh no, it's an ordinal, it's only 2.
How many ordinal numbers can be isomorphic to a well ordering on 2 element set?
1.
So therefore only 2. Yeah. So how can I well order 2 element set? Well, I can declare 2 less than 3. That is irreflexive transitive. That is in bijection with 0 comma 1. Yeah, 2 maps to 0, 3 maps to 1. And that is also an order isomorphism, right? It preserves and reflects order. Okay, so that's good. So S of X is equal to 2. Then let's say x is equal to rational numbers. Then what is S of x? Rational numbers can be well ordered. Yes, we have seen that zigzag argument. Yeah, so they can be well ordered. So what will their order type be?
Omega, omega plus 1.
Yes, so they can be listed. So once we know their listing, then we know that they can be well ordered using omega, like isomorphic to omega. Right? We have done that listing, yeah, when we did construction of rational numbers as pairs. Okay, then if it is in bijection with omega, then there is some other linear order. When we put that 0, the least element, at the end, then it is also in bijection with omega plus 1, like order preserving bijection. And dot dot dot, well, I will get all the numbers, yeah, omega dot 2, omega dot omega, and even epsilon naught, epsilon 1, and there is so much. Well, first of all, we should know whether S of x is a set and whether it is non-empty. So let us notice the set part first. Yeah, so note that S of x is a set since there could be at most power set of x cross x many well orderings of x. Every well order less than is a subset of x cross x, so therefore there could be only so many well orders, and power set of x cross x is a set. X is a set, so x cross x is a set, so power set of x cross x is a set. Yeah, our usual argument. So therefore Sx is a set. Why is Sx non-empty? Sx is non-empty thanks to yes, thanks to the well ordering theorem. Well ordering theorem says that there is at least one well ordering. So therefore Sx is non-empty. So now what happened? See, the answer is in front of you. Sx is a non-empty subset of On. Therefore Sx is a non-empty subset of On, and On is a well order. So therefore for every non-empty subset there must exist a least element. So the cardinality of x to be the least element in Sx. Well, okay. So, I mean like after forget and forget belongs to, yeah, this is in brackets. So therefore now observe this. What is cardinality of the set 2, 3? Sx was singleton 2. So cardinality of this 2 element set is 2. Well, I am saying it's a 2 element set, yeah, because that's how we are trained. Then cardinality of rational numbers is what is the cardinality of rational numbers? Omega. Yeah, omega is the least element in that collection. It cannot contain omega 1. S of q cannot contain omega 1 because omega 1 is the first uncountable ordinal, so it cannot contain omega 1. So this is omega, but like I said, forget the belonging relationship. So what should I write? Aleph naught. Very good. Well, what is cardinality of real numbers in that case?
2 per aleph.
2 to the power aleph naught, correct. Yes, 2 to the power aleph naught, which means the power set of natural numbers. Well, I haven't described the cardinal arithmetic, so let's do that quickly. Yeah, this is now very easy. So, cardinal arithmetic. And I'm going to say that assume well ordering theorem. I'll tell you at the end what goes wrong if we don't assume well ordering theorem. Okay, so suppose kappa and mu, these are cardinal numbers. Define kappa plus mu to be equal to maximum of kappa and mu. Very boring. So any two cardinal numbers are comparable. Yeah. So here I will write that. Yeah. Any two cardinal numbers are comparable, i.e. Cn with respect to belonging relationship is, satisfies trichotomy. You know what is trichotomy? Yeah? Given any kappa and mu, either kappa is equal to mu or kappa is less than mu, which is kappa belongs to mu, or mu belongs to kappa. Okay. So therefore, the sum is this. Then what is the product? Again, if kappa, I'm doing it for, and kappa and mu are infinite. Yeah, otherwise this is totally wrong. Yeah, I cannot say sum of two finite numbers is maximum of them. Yeah, so for finite numbers, this is the case. Infinite number. So maximum of this, and finally, kappa to the mu. Well, what is it? Well, maybe I should do something slightly different. Let me get rid of this for a moment. I will describe it in a different way. As follows. The answer is correct, yeah, that it will be plus. So let A and B be sets such that cardinality of A is equal to kappa and cardinality of B is equal to mu. Then define kappa plus mu as the cardinality of the disjoint union of A and B. Then kappa dot mu is the cardinality of, any ideas? Cartesian product of A and B. Very good. And kappa to the mu is the cardinality of, not power set, the set of functions from, not A to B, B to A. Yeah, because this is what we write as cardinality of, A to B. So what is this idea? I mean, in normal words, what we are writing, I mean that cardinality of A disjoint union B is cardinality of A plus cardinality of B. Cardinality of A times B we are writing as cardinality of A multiplied by cardinality of B, and cardinality of B to the power A is cardinality of B to the power cardinality of A. So if I ask you a simple question, so what is cardinality of R minus Q? Well, how do you compute that?
R minus Q is
So cardinality of R minus Q, I can find it out by doing this computation. So cardinality of R minus Q disjoint union the set of rational numbers is cardinality of real numbers, but this side is cardinality of R minus Q plus cardinality of Q. Okay, and this is equal to 2 to the aleph naught. Now you understand why I am writing 2 to the aleph naught? Because of this kappa to the mu. What is real? What are real numbers? Yeah, reals are in bijection with the set of functions from natural numbers to 2. Therefore, I am writing 2 to the aleph naught. Okay, so this is then this is aleph naught. So cardinality of R minus Q plus this is equal to 2 to the aleph naught. Now, in order to simplify this further, we will need some observations, and let's write them over here. If at least one of kappa and mu is infinite, then kappa plus mu is equal to kappa times mu. Oh, and both are non-zero. Yes, I need to be very careful. Oops, this is a very big eraser. Infinite and both are non-zero. Then kappa plus mu is equal to kappa dot mu is equal to maximum of kappa and mu. Because any two cardinal numbers are comparable, so it's just the max. Now, what does Cantor's theorem tell us? So Cantor's theorem tells us that the cardinality, any alpha, I mean aleph alpha is less than 2 to the aleph alpha, right? What was Cantor's theorem? That the cardinality of the power set is strictly bigger. What is power set? We have seen this, yeah, that power set is nothing but functions from that set to 2. So therefore, Cantor's theorem tells us that any cardinal number, yeah, I mean in other words I can say, or kappa is less than 2 to the kappa for every cardinal kappa. So this is true. Now what can you say about cardinality of R minus Q? Q and R minus Q are both infinite. So therefore that comment applies. The cardinality of both of them, the sum of them is going to be their maximum. Now we already know aleph naught is less than 2 to the aleph naught by Cantor's theorem. So therefore, what can be? Can cardinality of R minus Q be less than 2 to the aleph naught? No. If it is strictly less than, then the maximum of those two numbers is also strictly less than 2 to the aleph naught, which is a contradiction. So therefore, and can it be bigger? Obviously not. Yeah, I mean, if A is a subset of B, then cardinality of A must be less equal cardinality of B. You are supposed to prove this in the assignment. Yes. Then, so cardinality of this number is less equal to the aleph naught, and if it is strictly less than, then that is a contradiction. So therefore it must be. So this will imply that cardinality of R minus Q is equal to 2 to the aleph naught. I did not write the whole argument, but I invite you to do that. Yeah, please make sure you write this argument down properly. And one last thing I would like to say just in a minute, the continuum hypothesis or CH, it says that 2 to the aleph naught is equal to aleph 1. So it says that there is nothing, no cardinality between aleph naught and 2 to the aleph naught. That's an immediate successor. So aleph naught is the first infinite initial ordinal number, infinite cardinal number, and aleph 1 is the second one. So actually we cannot prove this statement or disprove this statement, right? So it is known, I think, that aleph 2 to the aleph naught is not bigger equal aleph sub omega, but which one, is it aleph 1, is it aleph 2, is it aleph 3, that one is not known. Yeah, we cannot commit to a position. And more generally, generalized continuum hypothesis, it says, this is a much stronger statement actually than continuum hypothesis, it's called GCH. It says that if alpha is an ordinal number, then 2 to the aleph alpha is equal to aleph alpha plus 1. So the power set of any infinite set is the immediate next cardinal number. Okay, one more thing before I wrap this up, that if you do not assume well ordering theorem or axiom of choice, then this statement fails, this green statement fails to hold. Cardinal numbers are still comparable, but cardinal numbers will still be comparable because they are subclass of ordinal numbers, but cardinalities are all over the place. So it's not necessary, if you do not assume axiom of choice or well ordering theorem, then it is not necessary that there exists some functions between any two sets. And if there do not exist any functions, then their cardinalities are here, there, yeah, they are not linearly ordered. So it's a very weird situation if you do not assume axiom of choice or equivalently well ordering theorem. Let's end it here.